Hello, Chem 20s. So today we are going to be going through acids and bases. You should have covered the basic review from Science 10, but we're going to look at Arrhenius acids and modified Arrhenius and Bronsted Lowry acids and bases today. So acids and bases in solution. What we've got is kind of the definition of when we first start here. Our understanding of what was done in Science 10. So acidic molecular substances, they ionize to form ions. That's why we have this term from solutions of ionization, because these form ions when they're in solution. So an example, HCl, hydrogen chloride gas. When it gets bubbled through water, what happens is it produces hydrogen ions and chloride ions. So we are forming ions. This is a molecular compound. It doesn't normally have ions. And when it's in water, though, it forms a different ion. Ionic substances dissociate in solution. So this is just what we've learned about. Ionization is this. Dissociation is when we have an ionic compound, and when it hits water, it dissociates into its associated ions. Okay, so Arrhenius acids. So the original Arrhenius theory of acids was any substance which ionizes to form hydrogen ions. So these H plus ions in aqueous solution. So that's kind of an important part there, understanding that we've got aqueous solutions occurring here. Okay, so this is when you get the acids by Arrhenius definitions. That's that AQ, and you get hydrogen ions. Bases are any substance which dissociate to produce hydrogen ions in aqueous solutions. So this was the original Arrhenius theory of acids and bases. The only problem with this, it kind of limits things like, well, for example, when we look at something in ammonia, we know ammonia is a base. And if we look at it, it's NH3. There's no hydroxide there or no OH. So how does this become a base? So what had to happen was Arrhenius had to modify his understanding and definitions of acids and bases. So here's the new thing that was created, the hydronium ion. So Arrhenius came up with this because hydrogen ions don't exist in isolation. Because a hydrogen ion is a proton and electron. If you take away that electron, it's just a proton. We don't have these just straight protons floating around. So what actually we get is these hydronium ions. So these H plus ions, these don't actually exist. So water and hydronium ions are attracted to hydrogen bonding. And hydrogen bonding, remember from when we learned about this in the bonding unit. So here's what our water molecule looks like. We have oxygen, and it's bonded to hydrogen and bonded to hydrogen, and it's got two lone pairs. Right? So remember back from the bonding unit, this creates a negative side and a positive side to the molecule, and that's what creates that strong hydrogen bonding. What hydronium ions are is you have oxygen, which has those lone pairs, and there's two lone pairs. It's bonded to a hydrogen, and it's bonded to a hydrogen. Now what happens is the hydronium has another just proton, so hydrogen, which bonds here. And that essentially creates a bond between the positive and the negative side. So you have now this hydronium ion, which overall has a charge of +1 because there's one more proton here than electron in this compound. So hydronium comes up a lot in this unit. Here's how we get the process of what happens and how the hydronium ion is produced. So example here, HCl, hydrogen chloride, sorry. So hydrogen chloride, it's a gas, and when it gets bubbled through water, what happens is the hydrogen chloride attaches to the water molecules, and you get these big intermediate molecules here. So you can see this is the HCl part, and this is the water part here. Okay. And what comes out as a result, this is where the term ionization comes from, because this doesn't produce any ions. When it goes through this process, it produces a chloride ion, and now you have the hydronium ion because that hydrogen here bonds to the water and leaves that chlorine alone, which becomes chloride. So modified Arrhenius is now a little different than what you've learned in Science 10. Before we just had hydrogen. Now Arrhenius definitions, you have hydrogen iodide or hydroiodic acid. When it mixes with water, it makes a hydronium ion and an iodide ion. Sorry. So this is what changes now. We now put the water in the mix and we create this hydronium and you have this other ion. Before you had just H plus, so now you get that. So this is kind of the big difference. Before we looked at it as they were splitting apart. Now we have to look at actual modified Arrhenius as there's a reaction occurring between the acid and the water to produce this hydronium and the reciprocal ion. So here's your hydronium. Okay, so non-metallic oxides. This is kind of the cool thing, and where this comes in weather and environmental stuff is something like carbon dioxide, so CO2. So carbon dioxide gas, it produces acid rain, and this is something you should have heard about before. This, what will do, it will react with water, and as a result, what it does, and this is what happens in the sky, is you produce carbonic acid. So this is how we have non-metal oxides, right? There's no metal here, it's a non-metal. Non-metal oxides, when they combine with water, they produce an acid. And now that acid, so this is your first step of when you're making an acid. This is step one. Step two, we have, um, sorry, we have carbonic acid, and it is going to react with water to now produce hydronium ions and a hydrogen carbonate ion. So a couple different things here. First thing, you'll notice this double-edged arrow. This is something that will come in our next lesson, explain what is happening here. This is the hydronium ion, and notice here how one hydrogen only leaves this carbonate. Here we had two, here there's one. So we don't get actually carbonate on its own initially in the first step. Only one hydrogen comes off in this process. And if you look on your periodic table and your polyatomics, you will see this in your polyatomic table, these hydrogen carbonates. And these are what they are. And when we start looking at weak acids, we'll understand this middle step of what's occurring. So Arrhenius bases dissociate with in water to produce hydroxide ions. So this guy, lithium hydroxide, produces lithium ions and hydroxide ions. But the nice thing about Arrhenius's modified definition is now we can look at something like this, NH3. So NH3, or ammonia, we classify that as a base because what happens is when it reacts with H2O, it produces ammonium. Dang it. Sorry, people. Ammonium, which is NH4. And, sorry, I'm having trouble with my pen, a hydroxide molecule. Sorry, so let me just try and write that out again. Obviously, eraser is not working for me. We've got NH4, which is aqueous, and also has a positive ion, and you have hydroxide. So this is the part that makes a base, this OH negative, this guy right here. So why that's important is we have this. Now this is what makes it a basic property, and then this ion's just present. But this is the part that makes a base. So when we start looking at the process of how this happens, the last one we looked at, we had a non-metal oxide makes an acid. So a metal oxide, right here, a metal oxide makes a base. So we have barium oxide, it reacts with water to make barium hydroxide. So now when we have barium hydroxide, here's our second step. This barium hydroxide mixes water to make barium ions and hydroxide ions. So metal oxides make bases, non-metal oxides make acids. So last thing we're going to look at today is Bronsted Lowry acid. So the last one we looked at was modified Arrhenius and Arrhenius acids. Bronsted Lowry acids, this is more a Chem 30 concept, but it's a good thing to take a look at. So a proton is represented by a hydrogen ion. Because when a hydrogen atom loses its electron, a proton is all that remains. So if we think of a hydrogen, right, we have hydrogen, it's got one proton, and it's got an electron on its end. If it loses that electron, all that's left is just that proton. So a Bronsted Lowry acid is a little different. An acid, a chemical species that loses a proton in a chemical reaction. So if we're looking here, we have two things. One of these is going to lose a proton, and it's this guy right here. If we look at the conjugate part here, this is HCl, it becomes just Cl negative. So this is our acid. And it becomes, this is the conjugate pair. So this guy, it now becomes the conjugate base, is what we call it, of this, because this one lost a proton, and this is its resulting partner of what comes from it. The Bronsted Lowry base definition is a chemical species that gains a proton in a chemical reaction. So if we look at these two here, this one, its conjugate pair is right here. And if we look here, this is a base. It gains a proton. That's why we add that H. So there's 3 H's here, there's 4 here. We get this plus. This now becomes your conjugate acid. So if we remember that definition and we look at what we just talked about, our Bronsted Lowry base is a species that gains a proton in a chemical reaction. So if we look back to our last one up here, we had this guy. And if we look here, it gains a proton. So this is our base in this reaction, and it has a conjugate acid right here. So in a Bronsted Lowry definition, there's always an acid, and a base, and then you have a conjugate acid and a conjugate base as a result. The acid will turn into the conjugate base, the base will turn into the conjugate acid. So if we look down at our second definition, we had NH3, it gained a proton, so the base and its conjugate acid. Well, this one, the acid definition is losing a proton. So HOH, or water, is now our acid, and it is going to lose a proton to make our conjugate base. So just paying attention to which one loses a proton and which one gains a proton, that's how you can identify what's an acid and base. So there's a little intro into what our Arrhenius definition is, our modified Arrhenius, and our Bronsted Lowry acids.